degrees Celsius. Calcium 750 to 800 is roughly when that happens. When that happens, free lime increases, right? CaCO3 changes to CaO plus CO2. CaO is free lime, that increases. Free lime increases during that time. And then you have silica, free lime combines with CaO to form C2S. C2S is the first compound that is formed in. There are reasons why I am going through this, but I'll talk about that. So C2S, dicalcium silicate, is the first compound that is formed, and that happens before 1000 degrees Celsius, 700 to 900 typically. Okay? Now, because you have calcination happening, if you're a process guy interested in cement manufacturing and knows where my temperature should come from, calcination is an exothermic reaction. Because your CaCO3 is becoming CaO and CO2, you have heat also being generated. Therefore, the process doesn't have to give external heat at that point. Your 850 degrees Celsius is roughly maintained in the kiln because of the exothermic reaction of calcination. Okay? So that is your first idea of what happens in the kiln. And basically what I have told you is when C2S forms. Okay? Now, at higher temperatures, you start to have sticky particles, reactions between solid particles will start to happen. Small B-lite crystals, B-lite again is C2S, A-lite is C3S, B-lite is C2S. B-lite crystals form from combination of silicates and CaO. From free CaO starts to go down. 1200 to 1350, more agglomeration, capillary force of keeping the liquid together. About 1250 Celsius, a liquid phase is formed because now you have melting that's happening, right? And what do you have in that liquid phase? C3A and C4AF. They happen in the liquid phase, and that liquid allows the reaction. Now, anytime when you make a dish at home, do you just put vegetables and boil it? You add water. Why? The heat transfer is always more efficient through a liquid than through a solid. If I put two solids together, there is only the contact points for heat to be transferred through. If I put it in a liquid, I have a much larger volume for the heat to transfer. Exactly the same idea. Right? Now, that is why you need to heat this to a higher temperature so that you get a liquid. So that heat transfer happens, and therefore C3S, A-lite is C3S, A-lite starts to form, because without C3S, it's very hard. Even though in Europe and in the US, they are making pure B-lite cements also, pure C2S cements also. Are they doing it in India? No. So they're doing pure B-lite C2S cements, because to get C2S, simple idea, right? I have heated till 1230, 1300 here. If you go back, if I want only B-lite, what am I heating up to? What do I save? A lot of energy, right? But C2S, what's the problem with C2S? Doesn't generate strength fast. So if you want only a very slow setting cement, actually what they do is B-lite and they do sulfur aluminates. They add different things to increase the strength and all of that. But generally, that's what you want. So A-lite crystals are formed at 1350 Celsius. So calcination, limestone becomes CaO and CO2. Clinkering reaction is where C2S and CaO become C3. So two important names, calcination and clinkering. Calcination is when lime forms. Clinkering is when C3S forms. Okay? So two important things that you have to. Clinkering ends when all CaO is used up. And then finally, with reaction, your allied crystals, your C3S crystals become larger. Clinker becomes nodule like that. So you get a nodule like this, which you will crush, and different zones. I'll skip these things. That's your clinker. You will crush the clinker and get what you call the cement. Okay? Grinding, I think it was there before. So you get C3S roughly 55 to 60%, C3S 15 to 20%, C3A 5 to 10%, C4A 5 to 8%, gypsum 2 to 6%. Now, that's a basic clinker. Here also, generally, you can make different grades of cement in two different ways. The first way is you can change the amount of C3S that forms by changing the chemical composition of what goes inside the kiln. So that you get a 53 or a 63 grade cement if you have a large amount of C3S that's forming, right? So you can change your raw material ingredients. I don't know if is that done in India? In some plants they do. US, nobody does that. They have just one clinker. They don't even touch or screw up with their chemical composition. There's only one cement. If you want a high early strength cement, what do? Just grind it finer. That's it. So grinding. So they don't play with the chemical composition at all. Every cement that comes in except high alumina and low alumina cements, because that you have to add alumina, you can't do anything else. But with strength, from a point of view of strength, you control the strength completely by particle size distribution, completely by the grinding process. The advantage? Easier to do because you're not relying on a chemical process which is slightly more tricky to manage. Mechanical engineers know how much load exactly to put in the grinder, how much of charge to put in the grinder to get different sizes. Very easy, very straightforward. Okay? So this is generally the composition that everybody will live with. And you will know a lot of these. C3S contributes to high early strength, C2S contributes to late age strength, C3A reacts with water immediately. In the absence of gypsum, C3A causes flash set, so you need gypsum for that. These standard pictures you will see in any kind of textbook. Okay, silica modulus, alumina modulus, lime saturation factor, undergraduate stuff, right? So you need to control these things in cement manufacture. Silica modulus, slow reaction of the silica modulus is high. Because if the silica is very high, the reaction is slow because silica is typically generally inert. You need it to be combined with something else to react. Alumina modulus, controlling the melt temperature. So if you have, you want to keep it around 2. Lime saturation factor, closely controlled between 0.92 and 0.96 because you don't want too much of free lime. Right? What happens if you have too much of free lime? Efflorescence. Okay, what else? Expansion. What else? Not enough strength. Right? So all of these, and then because of leaching, high porosity, all of those issues. Bogue's equations, all of you know Bogue's equations? Actually, I would recommend you not to study these equations, okay, and not to use them. They're generally wrong. For the kinds of cements that we make now, Bogue's equations gives, actually if you look at Bogue's equation, I didn't put the whole thing. They give you 2 different equations for 2 different C3A contents. I would rather do with this day and age when XRFs are common, XRF is cheap, I would rather do a direct chemical composition if you have to do. A lot of laboratories would be doing it rather than using Bogue's equation to predict the numbers because they're generally not correct unless you hit the exact range that Bogue says. He just did a lot of experiments and did some statistical fitting and got those equations. They may not be right for your case. It was good in 1950 and 1960 when we didn't have sophisticated instruments to measure, but now X-ray fluorescence is fairly cheap. When I say fairly cheap, not for individuals to buy, but for companies. And you can always, I'm sure cement plants, so every cement plant will have an XRF. A lot of testing companies now will have XRFs that you can go. A lot of XRFs are being used for environmental applications. Anybody who does things with geology has an XRF because they want to identify what minerals they have, right? So XRF is common. That's the best way to find out the composition than Bogue's equation. Clinker, the dark rounded particles is optical microscope. The dark rounded ones are C2S, the angular ones are C3S. This is the magnified version of a C3S crystal. So you always will hear, have you seen an X-ray diffractogram of a cement? An X-ray diffraction curve of a cement? Do you know what X-ray diffraction means? We'll talk about that when we get there. So if you see an X-ray diffractogram of cement, so X-ray diffraction is basically a technique to identify crystals. So you will see if you have a very pure crystal of something, you will see a very high peak in the diffractogram corresponding to the angle of diffraction of that crystal. In cements, you have so many different elements. Some of them are crystalline, some of them are amorphous, so you will get a number of different peaks. Okay? So C3S being crystalline, you will get a weak crystalline peak for C3S, even though we generally classify cements to be amorphous, because amorphous materials are more reactive. Crystalline materials are very stable, they don't react well. Okay? But you will have a small crystalline peak for C3S, one way of reactivity identification for a cement based on X-ray diffraction to see what level of crystallinity you have in your C3S. Fineness, of course, you grind and you get fineness. Blaine's fineness is what you guys use most of the time. All the laboratories have Blaine's fineness. If you have a particle size analyzer, a laser particle size analyzer, you can get some nice cumulative size distribution curves which you would want for several applications. Now I think pretty much everybody has a size distribution analysis, because if you want to know what the how fine and what kinds of particles you have in your cement. Fineness, finer cement, faster reaction. So it has to be good, right? No? What's wrong with faster reaction? More heat of hydration. Problem with more heat, what happens? Likely to crack if you don't have enough heat transfer to the outside. Large particles do not react with water completely, which is perfectly fine. I mean, you always can think of a cement particle from an economics point of view. Okay, again, I'll use the food analogy here. You go to a restaurant, you eat buffet. Would you eat the whole thing? You would eat only what you want. You need only as much hydration as you want. The rest can stay there. You don't have to have the entire cement particle hydrated. Now, some people will argue, no, that's not right, because I'm paying so much for the cement and I'm not letting it hydrate, it's being wasted. Right? That's an argument which is I think a valid argument. That's when you should look at designing systems with other inert materials. And I'll show you some examples of what we have done with limestone, with inert limestone powder, where you can add limestone and let the cement hydrate and have limestone act as what we call the nucleation sites for cement hydration. I'll show you that probably tomorrow. So there are a lot of ways of doing it to control that. Again, that's why I said it's a designed product rather than a random sequence of things. Okay. Any questions? You know what? One of the things when I ask you any questions, there is a sinister intention behind it. I need to catch my breath too. So you have to ask questions. If you have nothing, I need to go on. I need to have energy to do that. So ask something so that I can catch my breath and pretend that I'm thinking. Right? No questions so far? Okay. Either I've taught you really well, or you know all of this before, or no, I don't want to tell you a third case. We'll leave it. Okay. So we'll start with hydration. I know how much more time is Dr. Das around here? No. How much time do we have? Till 1:30? So I have another 40 minutes. Okay. I think I can complete most of hydration today. So I'll give you a few things about hydration that you probably wouldn't have seen before. So basically you have reaction between all these different crazy substances with water and forming some glue, and that glue binds everything together, and after some time when you come back, you get a very strong, durable material which you can use for whatever application that you have designed it for. Okay. Hydration is a chemical reaction. right? It's a complicated chemical reaction. It's not like NaCl plus H2O giving you something else. It's a more complicated chemical reaction. But every chemical reaction, I want you to emphasize these three different things: change in matter, change in energy, and the speed or kinetics of reaction. Everything, your entire microstructural development starts right here. Okay? This is where everything starts. You think you're mixing cement with water and you poke your finger and you feel heat. You said, oh, that's heat of hydration. Good. I don't need anything to measure it. I feel that there is heat. And you put it for a longer period of time. You feel burn in your hands and you think, okay, this is a very good cement, right? The idea is you have to start giving less and less importance to cement and more importance to what forms when cement reacts. So this is in two ways. For a cement manufacturer, this works both ways. For a cement manufacturer, now he can use that argument and says, don't blame me about my cement. It's not the cement. It's about what reacts with it. So you check all the cocktail of things that you have in your things so that it reacts well. For his benefit, he can say that, yeah, it's what causes when it reacts. Therefore, you should have a good cement to react. Right? So with both ways. But change in matter, if you look at it, what formed when cement reacts? What forms when cement reacts with water? What forms? CSH, then calcium hydroxide, and voids. Correct. Voids. They also form, right? You create space where there was no space, where there was water basically, you create space. And that creation of space, that change in matter that created the space is going to be the detriment in most cases, whether it is for strength or for durability. Right? So changes in matter very important. Now change in energy, heat. Amount of heat that is released. Sometimes heat is good. Sometimes heat is not very good. If you're really doing a cold weather concreting, you want your concrete to generate as much heat as possible. If you're doing really, really hot weather, you want it to be as cool as possible. So change in energy. Now, you all know that energy cannot be created nor destroyed. If you believe in Albert Einstein, energy is a function of mass, right? Then mass is nothing but matter. Therefore, my first point, changes in matter influences changes in energy, right? So those are mutually dependent points. So you will have energy. Again, that is why cement chemistry and reaction is all about thermodynamics. Sadly, and I have argued for this to as many IIT heads of departments, as many faculty that I can see, that thermodynamics should be made a mandatory course for civil engineers. Nobody listened. In the US, thermodynamics is mandatory for civil engineers because if you're studying environmental engineering, you can't study environmental engineering without thermodynamics, without chemical kinetics, right? But in India, thermodynamics apparently is only for mechanical engineers and we don't study it. Now, I didn't study as an undergraduate while I was doing my BTech from here, and I had to go to US and struggle in classes that required me to have thermodynamics, and I was struggling to figure out what this is. Then of course I took additional classes and made up. But thermodynamics, heat and energy, mass transfer is what is happening in any chemical reaction. If you want to know concrete, if you want to know concrete well, if you want to understand and design concrete well, thermodynamics becomes a very important component. So I'll give you some initial energy transfer things for you to just get a feel for. In 5 days, I can't teach you a whole course, but I'll just give you a feel for those things also. And then speed of reaction, chemical kinetics, which means how fast your cement reacts, setting, hardening, which is important for field use. Okay, again, these are all the equations that you can go through, which is fairly complicated, but we'll go one by one. Okay. Now, where's my, oops. Two different things happens when cement reacts with water. Again, this is the core of microstructure formation. So let's don't think about too many cement. Just think about one particle of cement in an infinite ocean of water. That's easy to understand. We call it an infinite dilution. One particle, as much water as it can take to react. So there's no competition, no fight between particles for water, right? Typically, if you're doing a high performance concrete, water cement ratio will be what for high performance concrete? 0.3, 0.35. There is a lot of competition for water between the cement grains, right? And that's why some grains will hydrate, some grains will not. Now, you have no competition for water. So if you have an infinite dilution case, you have two complementary and sequential reactions that are happening. You have the cement particle, it reacts with water, water comes in contact with the outside of the cement particle. What do you have in a cement particle? All these different ions, right? Calcium and silica and aluminum and all of that. When you hit sodium, when you put salt, when you add a drop of water to salt, what does salt immediately become? Salt ionizes, right? It becomes ions. Ions of what and what if it's salt? Ions of sodium and Na plus and Cl minus. Very similarly, you have ionization process or dissolution of cement grains into its ions that will go into the water, into the solution. The water that you add ceases to be the water anymore, it becomes an ionic solution. The strength of that ionic solution depends on how much ions have come from water to the cement. When enough ions come from the cement to the water, you will say the solution is saturated. When the solution is saturated, it cannot accept any more ions because it is no more in equilibrium. If it is not in equilibrium, any material in the world, any system in the world, our only tendency is go back to equilibrium. Why? Equilibrium is a state with the lowest energy, right? We all want to be in the lower state of energy, right? If you can afford to sleep, will you sit up? You'll go and sleep. Why? Lying down is the lower state of energy. Now again, I use this example if you're watching TV in the night, okay, you're sitting in your living room, you're watching TV in your living room, 11 o'clock, you're feeling very sleepy. Sitting down and watching TV, very sleepy, low state of energy, right? But you have to go to a bedroom and sleep. Can you be transported from your sitting room to bedroom without spending energy? You have to get up and walk. Getting up and walking to do what? From a lower state of energy to an even lower state of energy, you want to overcome an energy barrier. Every material, every chemical reaction, every day faces this energy barrier. And that energy barrier is what won a guy called Arrhenius a Nobel Prize. Okay? This energy barrier. So you cannot go, I'll say, simply you cannot go from sitting to sleeping without walking to your bed. That's a simple example. Sitting is comfortable, but not as comfortable as sleeping. Sitting to sleeping cannot happen without walking. You have to overcome an energy barrier. That is what chemical reactions are all about, cement hydration is all about. You know the energy barrier, you solve the equations for energy barrier, that's all you want to know. You can create any kind of cement and any kind of hydration reactions ever, that's all. One word of hydration, overcoming the energy barriers. Okay? Every reaction, because the tendency of any material is to go down to its lower state of energy. The whole world is a sphere because sphere is a shape with the lowest surface energy, right? A water droplet, when it falls on a leaf, assumes a spherical shape because spherical shape is a shape with the lowest energy. Everybody wants to go down to the lower state of energy. Two atoms combine to form a molecule because the molecule has a lower state of energy than the atoms themselves. Atoms have electrons running around, jumping around from one shell to the other. Once you share those electrons, stop them from running around, they go down to a lower state of energy. So chemical reactions are all about lower state of energy. So when you mix cement with water, it's immediately saying, okay, I need now to go to a lower state of energy. What's the way to go to a lower state of energy? I have to get rid of my ions. That ions have to go into the solution. Now the solution says, okay, you have dumped me with all these ions. I am saturated. When I am saturated, I cannot accept anymore. What should I do then? Precipitate more. Is that not happens everywhere? Right? Dissolution, saturation, precipitation. That's it. Energy barrier, dissolution, saturation, precipitation, hydration done. That's hydration. Simple chemistry of hydration, of course. And then you have to add the different bells and whistles to it. So the structure is formed. The basic structure is happening when you have the ions dissolving and precipitating back. The precipitated particles are called your CSH or CH, depending on what you have. And the space that did not get occupied by the precipitate stay as voids or porosity. Sounds good? Okay. So C3S, simple. If you do C3S reaction, 2 moles of C3S reacts with 11 moles of water to form 3 moles of CSH. I said C3S2H8 for simplicity. It's not exactly like that. So C over S ratio of 1.5, which is generally what you see in cement systems, plus 3 moles of calcium hydroxide with a heat of hydration of 173.6 kilojoules. If it is C2S, you again get 2 moles of C2S, consumes less water. See that? Consumes less water. Does anybody want to guess the reason for this consuming less water? Huh? Did I see a picture? Did I show a picture before to see that? What was the shape of the C2S? Round. C3S? Angular. So, because of the spherical shape, lower surface area, it can take only lesser amount of water, and you get the same amount of CSH, plus the amount of CH is lower, and you have only about a third of heat of hydration. So there is no wonder that you would want more C2S if you want to control the heat of hydration. If you want mass concrete, if you are concreting a 2-meter thick wall, you want more, because again, if you are doing a wall, you probably wouldn't want 40 megapascal strength the next day. You can afford to have long-term strength gain. Therefore, you would want more C2S. More C2S, less heat. More C3S, more heat. Right? All of these are concepts that you have gone through. Again, aluminates forming. I don't want to go through and complicate this, but ettringate, monosulfur aluminate, tetracalcium aluminohydrate. You know all of these, right? Oops. 2 mechanisms of reaction.